Welcome back to Practical PyTorch. In this video, you'll learn how to combine two tensors, adding them cell by cell, stretching different shapes to fit, summing along an axis, and the matrix product. Let's start with something that shouldn't work. We have a grid of 12 numbers, 3 rows and 4 columns called scores, and a column of just 3 numbers, 10, 20, 30, a completely different shape. Now we add the grid and the column together and print the shape of the result. No loop, no error. It just ran and the answer is 3 by 4. 2 different shapes added and it worked. A rule called broadcasting decided that. By the end of this video, you'll know exactly how. This video has 4 parts. First, element-wise operations, same shape in, same shape out. Second, broadcasting, how PyTorch stretches a size of 1 to make 2 shapes fit. Third, reductions, you name an axis and PyTorch removes it. And fourth, Matmul, the matrix product, where the inner numbers must match. Let's start with the simplest case. 2 tensors that already have the same shape. Let's start with one grid of numbers. We call it A. Its shape is 3 by 4. Remember, the shape is just the size along each axis. 3 rows, 4 columns, so it holds 12 numbers, starting from 1 in the top left. The first row runs 1, 2, 3, 4 left to right. Now a second grid, B, with exactly the same shape. Look at the top left cell of A, it holds 1. The top left cell of B holds 10. These two get added together and that's it. Every cell of O is added to the cell in the same position. In B, nothing else touches it. And the result, 1 plus 10 is 11, sitting in that same top left spot. The result has the same shape as the inputs, 3 by 4. This is an element-wise operation. Element-wise means it works on one position at a time. 3 by 4 plus 3 by 4 gives 3 by 4. Let's run it. We build our 2 grids. A runs 1 to 12 and B is all 10s. Then we print a plus B. 12 numbers come out, 11 through 22, added cell by cell. And the shape stays torch size 3, 4, 12 numbers in, 12 out. The same rule works for every operator. A minus B subtracts, cell by cell. A times B multiplies, cell by cell. A divided by B divides, cell by cell. And it is greater than 6 compares, cell by cell. All 4 give shape 3 by 4. Only the last one changes the D type. A is greater than 6 comes back as bool, true, or false. What if one side is just a single number? Let's try a times 2. Every cell doubles, 2, 4, 6, and so on across the whole grid. A plain number works against any shape, and that's the smallest version of the rule we're about to meet. So one number can spread across a whole grid. Broadcasting is that same idea made general. Back to our grid scores, which is 3 by 4. We add bias, a column of 3 numbers, 10, 20, 30. 10 landed on every cell of row 0. 20 on row 1, 30 on row 2. 3 numbers reach 12 cells. So how did PyTorch decide that? The rule has 2 steps. First, line the shapes up from the right. If one is shorter, pad it with ones on the left. Second, in each column the sizes must match, or one of them must be 1. A 1 gets stretched to the other size. So 3 by 1 and 1 by 4 line up as 3 against 1, then 1 against 4. Each side has a 1, so each side stretches. Let's watch that happen. A column of 3 numbers 10, 20, 30. Its shape is 3 by 1. And a row of 4 numbers 1, 2, 3, 4. Its shape is 1 by 4. 7 numbers in total. Neither one is a grid. The empty space is where the answer will go. The column has only one column, so it stretches out to 4. These dashed cells are copies of the same values. And they're read, not stored. PyTorch just rereads the same 3 numbers for each column. Now the row. It has only one row, so it stretches down to 3, more dashed copies. Now both sides are 3 by 4, and every position has a partner. Now it's an ordinary element-wise add. 10 plus 1 is 11 in the top left. The result is 3 by 4. Notice the answer is bigger than either input. 3 by 1 plus 1 by 4 gives 3 by 4. Now the important part. Those dashed cells never exist in memory. PyTorch reads the same 3 numbers again for each column. So a bias of 3 numbers still costs 3 numbers. Broadcasting adds no extra memory. But broadcasting can refuse. This is bad, a plain list of 3 numbers shape 3. We try to add it to scores, which is 3 by 4. And we get a runtime error. The size of tensor A, 4, must match the size of tensor B, 3. Line them up from the right, 4 against 3. Neither one is 1, so there's nothing to stretch. Now a trickier case. Pred is a column of 3, shape 3 by 1. Target is a plain list of 3, shape 3. We subtract them and print the shape. And it runs, but look, the shape is 3 by 3, 9 numbers. The rule found a 1 on each side, so it stretched both. 3 predictions, 3 labels, and 9 differences you never asked for. Let's turn that difference into a loss. We square it and take the mean. Then the same thing, but first we reshape target to 3 by 1. Both lines run. Both print one number, 0.32 and 0.57. Only the second one is your real loss. The first trained on nonsense, with no error and no warning. Give target the shape 3 by 1, and the bug is gone. One habit stops all of this. Print the shape after any line that mixes 2 tensors. It costs 1 line, and it catches the wrong shape right where you made it, not 10 lines later. It's the same habit as printing the D-type in the last video. You've combined 2 tensors. Now let's go the other way and collapse one tensor down to a summary. Back to one grid, X, 3 rows and 4 columns. A reduction adds numbers up. X.sum with no dim adds every cell into one number, 78. Now X.sum dim equals 0. The 3 rows fall together, 1 column at a time. In the first column, 1 plus 5 plus 9 is 15. 4 numbers survive, 1 per column. The shape is 4. Change it to dim equals 1. And now the 4 columns fall together, 1 row at a time. In the first row, 1 plus 2 plus 3 plus 4 is 10. 3 numbers survive, 1 per row. The shape is 3. Now the part people get backwards. Dim names the axis that gets removed, not the one you keep. 3 by 4 with dim equals 0 gives shape 4. With dim equals 1 it gives shape 3. Let me say it the other way too. Name dim 0 and the rows disappear. Name dim 1 and the columns disappear. Let's print both. We build X 1 to 12. x dot sum dim equals 0, and x dot sum dim equals 1. 4 numbers from dim 0, 15 up to 24. 3 from dim 1, 10, 26, 42. 15 was the first column, 10 was the first row. Sum isn't special. X dot mean dim equals 1 averages each row. And x dot max dim equals 1. Mean gives 3 averages, but max gives 2 tensors, the values and the indices, which tell you where each maximum was. Column 3 wins in every row here, so the indices come back 3, 3, 3. Now a quiet trap. X dot mean dim equals 0 gives 1 number per column, 4 numbers. X dot mean dim equals 1 gives 1 number per row, 3 numbers. Both lines run, both give a tensor. If each row is a student, only dim equals 1 is the average score per student. The shape 4 or 3 is the only warning you get. Now keepdim. First, the shape of x dot mean dim equals 1. Then the same call with keepdim equals true. The first is torch size 3. Its ndim dropped from 2 down to 1. The second is torch size 3, 1. The ndim stayed at 2. Same 3 numbers both times. Keepdim equals true just leaves the axis in place with size 1. Why would you keep it? Let's try subtracting the row mean from x is 3 by 4, and the mean is shape 3. And we get the same runtime error as before. 4 against 3, nothing matches. Line them up from the right, 4 against 3. The axis you removed is exactly the one you needed back. Add keepdim equals true, and now the mean is 3 by 1. Now it broadcasts. Every row comes out centered on 0, minus 1.5, minus 0.5, up to 1.5. 3 by 1 against 3 by 4 has a 1 to stretch, so use keepdim equals true whenever a reduction goes back into the tensor it came from. One more operation, and it's the one deep learning is built on, the matrix product. Let's start with a small square, as watch the difference between two symbols. S times S with a star multiplies cell by cell, 1, 4, 9, 16. But S Matmul S with the @ sign is completely different. This is the matrix product. That 7 is row 0 times column 0, 1 times 1 plus 2 times 3. So the star multiplies cell by cell. The @ sign takes a row times a column and adds it all up. Let's see the shapes. This is A, a grid of 12 numbers shaped 3 by 4. And B, a taller block shaped 4 by 2. Line the shapes up, 3 by 4 and 4 by 2. The two inner numbers are both 4, so they meet. Take row 0 of A, 1, 2, 3, 4. And column 0 of B, which is all ones here. Multiply position by position, then add it all up. 1 plus 2 plus 3 plus 4 is 10. That's one output cell. The other 5 follow the exact same rule. Every output cell is another row times a column. This is the whole result, see. 10 in the first row, 26 in the second row, and 42 in the third. The result is 3 by 2. Matmul joins the shared axis. 3 by 4, Matmul 4 by 2 is 3 by 2. The inner 4s meet and vanish. The outer 3 and 2 survive. In code, scores is 3 by 4. W is 4 by 2, all ones. Scores Matmul W, and we print the shape. Torch size 3, 2. Say it as a chant. 3 by 4, 4 by 2, 3 by 2. The two 4s meet in the middle and disappear. Let's check the actual numbers. We print scores Matmul W. 10, 26, 42, each repeated across two columns. W is all ones, so each output is just a row sum. Those are the same three numbers as x dot sum, dim equals 1. Now let's break it on purpose. Scores 3 by 4, Matmul a block that's 3 by 2. Runtime error. Mat1 and Mat2 shapes cannot be multiplied, 3 by 4 and 3 by 2. Read the two middle sizes, the 4 and the 3. They don't match, so there's nothing to multiply. You'll meet this error a lot. Let's put all three together. First, scores plus bias, that's broadcasting. Then take the mean along dim 1, that's a reduction. Then scores Matmul W, that's the matrix product. A quick reminder of the shapes. Scores is 3 by 4, bias is 3 by 1, and W is 4 by 2. Now watch the shapes. We start with scores 3 by 4. After the bias, still 3 by 4, Elementwise kept the shape. After the mean, shape 3. The reduction removed an axis. After the Matmul, 3 by 2. The Matmul traded the 4 for a 2. Your turn. We add zeros of shape 3 by 1 and zeros of shape 1 by 4. Does this run and what shape comes out? Pause and guess. Okay, here it is. It runs and the shape is 3 by 4. Line them up from the right, 1 against 4, then 3 against 1. Each side has a 1, so each side stretches. The answer is bigger than both inputs. Let's recap the 4 rules. Elementwise keeps the shape, a plus B cell by cell. Broadcasting lines the shapes up from the right and stretches a 1. A reduction removes the axis you name. X dot sum, dim equals 1. And Matmul joins the shared axis. 3 by 4, Matmul 4 by 2 is 3 by 2. So now you can put two tensors together, but there's one more thing they need in common. Every tensor sits on one device, the CPU or the GPU. Two tensors on different devices refuse to touch, whatever their shapes are. That's the next video, but first try it yourself. Lab 1, Shapes and Broadcasting, is where you'll break these shapes on purpose.